Last year, the James Webb Space Telescope began transmitting breathtaking images of the universe, showcasing humanity's ability to peer into the cosmos with unprecedented clarity. Positioned with its back to the sun, it shields itself from our star's intense light, allowing its massive golden mirrors to focus on the faint, red-shifted light emitted 13.5 billion years ago in the universe's infancy. This cryogenically cooled instrument captures the distant glow of the early universe, marking a monumental achievement. But what if we could go further, beyond the capabilities of even the James Webb? What if we built a massive radio telescope in space to detect signals from hydrogen atoms in the primordial universe, signals too faint for the James Webb to capture? Such a telescope could unlock secrets from the dawn of time, but constructing one presents immense challenges. On Earth, radio telescopes are colossal. The Arecibo Observatory in Puerto Rico, with its 300-meter dish, was a giant until it collapsed in 2020 after 57 years of service due to snapped support cables. That telescope used a natural sinkhole to shape its spherical dish, but Earth's atmosphere blocks the faint radio waves from the early universe. A bold new proposal from NASA scientists suggests building a radio telescope on the far side of the Moon, using a lunar crater as a natural bowl. This would be the largest space telescope ever constructed, potentially at a fraction of the James Webb's cost, and it could revolutionize our understanding of the cosmos. The concept of a massive radio telescope isn't new. The Arecibo Observatory demonstrated the power of large-scale dishes, but the proposed lunar telescope would dwarf it, utilizing a 1.3-kilometer-wide crater to suspend a dish 50 meters larger in diameter than Arecibo's. This idea stems from NASA's program encouraging researchers to envision futuristic technologies plausible within the next 10 to 20 years. Building on the Moon, however, is no small feat. The core innovation lies in using a lunar crater as a natural support structure, eliminating the need for heavy frameworks. The telescope's dish would be made of lightweight wire mesh, sagging naturally under the Moon's gravity to form a reflective surface. This mesh, with gaps smaller than the wavelength of incoming radio signals, reflects those waves just as a microwave screen mesh allows visible light to pass but reflects longer microwaves. The design drastically reduces weight, a critical factor given the high cost of launching materials from Earth. Selecting the perfect crater is a critical step. Since 2009, data from the Lunar Reconnaissance Orbiter has helped scientists narrow down candidates. The crater must be on the far side of the Moon, which is tidally locked to Earth and thus shields the telescope from Earth's radio noise. The farther from the near side, the better the isolation from interference. The crater needs to be roughly 5 kilometers in circumference and 175 meters deep to accommodate a 350-meter-wide dish. It should have a smooth interior free of large boulders or mounds, with a level rim for anchoring wires. Additionally, the telescope must point away from the Milky Way's noisy center to capture the faint radio waves from the early universe. Since a crater can't be repositioned, the telescope relies on the Moon's natural motion to sweep a section of the sky. A crater located between 10 and 20 degrees north offers the best chance to avoid galactic noise. From 82,000 craters on the Moon's far side, only 300 meet these criteria. And after further analysis, 50 were shortlisted, with one at nearly 10 degrees north selected as the prime candidate. The telescope is designed to capture radio waves in the 4.7 to 47 MHz range, corresponding to wavelengths of 6.4 to 64 meters. This imposes specific engineering constraints, as the dish must reflect and focus these waves to a receiver suspended within the crater. While mass isn't a major issue for a stationary lunar structure, minimizing weight is crucial to reduce launch costs. Lightweight carbon fiber cables, resistant to the Moon's extreme temperature swings from -70 degrees Celsius to 120 degrees Celsius, form the support structure. These cables anchor to the crater's rim, with the wire mesh sagging naturally to create the dish. However, a wire hung between 2 points forms a catenary curve, unsuitable for focusing radio waves. To achieve a parabolic shape that focuses waves to a single point, Engineers plan to strategically distribute weight along the wires, either by varying the wire's thickness or coating it with materials of different densities. This creates a shape closer to a half circle, optimizing the telescope's performance. Deploying this structure on the moon poses significant challenges. The lunar regolith, or surface soil, is razor-sharp and abrasive, requiring careful handling to avoid damaging the wires. The moon's gravity, about 1/6 of Earth's, makes supporting the structure easier. A 200-kilogram telescope on the moon feels like 32 kilograms on Earth. Several deployment methods are under consideration. One involves dual-axle robots developed by NASA's Jet Propulsion Laboratory, towing wires into place. Another proposes forming the wire structure above the crater before landing, either by a lander firing anchors or multiple landers positioning themselves at anchor points. The most cost-effective option, estimated at $2.4 billion compared to the James Webb's $10 billion, involves a single lunar lander at the crater center firing anchor projectiles to the rim. These anchors, similar to bolts, dig into the regolith upon tensioning. However, this method requires extensive testing to ensure reliability, as the abrasive lunar terrain could cause failures. Using rovers to deploy wires increases cost to $4.5 billion, making the projectile approach more appealing despite its risks. Once the anchors are set, they form the skeleton of the telescope. The antenna receiver is raised to the dish's focal point, either by tensioning wires from the anchor points or using a robotic pulley system that climbs the anchoring wires to avoid friction with the regolith. The reflector mesh, made of ultralight gold-plated molybdenum, is then deployed. Inspired by origami techniques used in space missions for solar arrays and heat shields, the mesh is folded compactly within the lander and unfurled by guide wires pulled to the top of the anchor cables. This allows a 350-meter dish to fit within a confined spacecraft, solving the challenge of transporting a massive structure. Unlike the James Webb, which produces stunning images, this telescope will collect data on hydrogen distribution in the early universe. Hydrogen atoms, abundant before stars formed, emit radio waves at a specific 21-centimeter wavelength when excited by collisions and subsequently decaying. By detecting these signals, the telescope can map hydrogen across space and time. Redshifting, caused by the universe's expansion, stretches these signals to longer wavelengths, allowing scientists to determine their age and track the universe's evolution. This data will test assumptions about hydrogen's uniform distribution, similar to how cosmic background radiation was once assumed uniform but later found to vary. The telescope's one-year mission is expected to gather enough data to refine models of star formation and the universe's cooling after the Big Bang. Transmitting data back to Earth requires overcoming the communication barrier posed by the moon's far side, which blocks direct contact. The Apollo missions faced this issue, and while China's 2018 relay satellite at the Earth-Moon L2 Lagrange point enabled communication with their 2019 Farside lander, NASA and the European Space Agency will need their own relays. NASA's Artemis program, focused on lunar exploration, will likely improve communication infrastructure, making data transmission more feasible. Beyond hydrogen mapping, the telescope could detect magnetic fields of exoplanets by analyzing how radio waves are altered as they pass through them, potentially identifying planets capable of supporting life. The team has already mapped exoplanet systems within the telescope's field of view, highlighting its broader scientific potential. The project's design will be prototyped using computer-aided design, CAD software, such as Onshape, a cloud-based platform that allows global collaboration on designs without file management issues. Onshape's browser-based interface supports various devices and complex tasks like finite element analysis, making it ideal for both professional and hobbyist engineers. This lunar radio telescope represents an ambitious leap in our quest to understand the universe. By leveraging the moon's unique environment and innovative engineering, it could unlock secrets from the earliest moments of cosmic history, all at a potentially lower cost than the James Webb. The prospect of building the largest space telescope on the moon's far side is not just a scientific endeavor, but a testament to human ingenuity and our unrelenting curiosity about the cosmos.